Hello friends, in the last class we have studied about that series magnetic circuits and solved some problems on series magnetic circuits. Now we will try to solve some problems on parallel magnetic circuits. Series parallel magnetic circuit. See here, this core is having this limb and this limb in parallel, which is connected in series to this limb. A magnetic circuit having two or more than two paths for magnetic flux to flow is called a parallel magnetic circuit. Here this limb is having an area of cross section of A1 and a length of L1, while this limb is having area of cross section A2 and length L2, while this path is having a length of L3, area of cross section A3. When a coil is wound on this limb, which is having a number of turns N, and when we are passing a current through the coil, a flux is developed from there which passes through the entire core. Here in this core, the total flux developed is phi1, which comes here and divides it into two depending upon the reluctance of these two paths. So flux passing through this path is phi2 and this path is phi3. So the flux coming from this path is in series with these two parallel paths. So this circuit can be called as a series parallel magnetic circuit. Before going into studying that detailed explanations and problems, it will be better to note the formulas we have studied about magnetic circuits in a piece of paper and keep it aside so that it will be helpful for reference. Comparison of electric and magnetic series parallel circuits. We have studied earlier that in many cases a magnetic circuit is analogous to an electric circuit. In the case of this electric circuit, the total current coming from here divides into two as these are two parallel paths. That is, total current I is equal to I1 plus I2. Then the total equivalent resistance R is equal to R1 and R2 in parallel plus this series resistance R. We know that R1 parallel to R2 is equal to R1 R2 divided by R1 plus R2. Therefore, this R equivalent becomes R1 R2 divided by R1 plus R2 plus this R. In the magnetic circuit, reluctance of this path is S, reluctance of this path is S1 and the reluctance of this path is S2. This mm of Ni is analogous to em of E in the case of this electric circuit. Similarly, S is analogous to this resistance of the electric circuit. This S1 is analogous to R1 of this electric circuit. S2 is analogous to R2 of this electric circuit. In the case of electric circuit, I is equal to I1 plus I2. Similarly here, total flux phi is equal to phi1 plus phi2. Req is equal to R1 parallel to R2 plus series resistance R. Similarly, in the case of this magnetic circuit, Seq is equal to S1 and S2 which are in parallel plus this series reluctance S, as S1 parallel to S2 is equal to S1 S2 divided by S1 plus S2. This equivalent reluctance Seq becomes S1 S2 divided by S1 plus S2 plus this series reluctance S. Let this is equation number 1. We know that reluctance S of a magnetic material is equal to length of the magnetic material divided by mu0 into mu r into area of cross section of that material. Mu0 is permeability of free space, mu r is the relative permeability of that particular material. Therefore, here this S is equal to L by mu0 mu r into A. S1 is equal to L1, that is length of this limb divided by mu0 mu r1 into A1, area of cross section of this limb, and S2 is equal to L2 divided by mu0 mu r2 into A2. In this electric circuit, E is equal to I into R. Similarly, in magnetic circuit, magnetic motive force F is equal to phi into S, that is total flux into reluctance S. Therefore, E1 is equal to, that is voltage drop across this path is equal to I1 into R1. Similarly, here F1 is equal to mm of across this path is equal to phi 1 into S1, and in this path E2 is equal to I2 into R2. Similarly here F2 is equal to phi 2 into S2. As these branches are parallel, even voltage drop across this path and this path will be the same. Similarly, in magnetic circuit, mm of F1 is same as this parallel path F2, but E1 is I1 into R1. Therefore, I1 into R1 is equal to I2 into R2. Similarly, here F1 is equal to F2. F1 is phi 1 into S1, that is equal to phi 2 into S2. We know that current I is equal to E by R. Similarly, flux phi is equal to mm of F divided by reluctance S, that is F is N into I by S. Bringing reluctance S to this side, mm of F is equal to N into I, that is equal to phi into S. Let this is equation number 2. Therefore, total mm of N into I is equal to phi into S plus phi 1 into S1. As this and this are same, this can be written as or total mm of N into I is equal to phi into S plus phi 2 into S2, since phi 1 S1 and phi 2 S2 are same. Comparison of electric and magnetic series parallel circuit with the air gap. Here consider a magnetic core in which two limbs are in parallel and there is an air gap in the middle limb. Area of cross section of which paths are: the main limb is having an area of cross section A, air gap is having a area of cross section AG, the left limb BAFE is having area of cross section A1, and this is having an area of cross section of A2. The length of the central limb is L, left path is having a length of L1, this path is having a length of L2, and air gap is having a length of LG. The reluctance of this main path is S, BAFE is having a reluctance of S1, and this limb is having a reluctance of S2, and the air gap is having a reluctance of SG. When the central limb is bound with a coil which is having a number of turns N, and when we are passing a current I through the coil, a flux is developed here and it divides it into these two parallel paths. The total flux developed in the middle path is phi, which divides into phi 1 through the path BAFE and phi 2 through the path BCDE. This is almost similar to an electric circuit in which there is a battery in the central limb and these resistances. The resistances are, here it is R, then in series one RG, and path BAFE is having a resistance of R1 and BCDE is having a resistance of R2. The main resistance R is analogous to the reluctance S of this path. In resistance RG in electric circuit is analogous to reluctance SG of that air gap in magnetic circuit. Resistance R1 of BAFE is analogous to reluctance S1 of path BAFE in the magnetic circuit, and resistance R2 of BCDE is analogous to reluctance S2 of path BCDE in the magnetic circuit. This EMF E is analogous to the mm of N into I created by the coil. Current I passing through the central limb is analogous to the main flux phi in the magnetic or central limb. Current I1 passing through BAFE is analogous to flux phi 1 passing through the path BAFE in the magnetic circuit. Similarly, I2 is analogous to phi 2 of this magnetic circuit. So, reluctance of path BG, this path is equal to S is equal to length L by mu 0 mu r into area of cross section A. Reluctance of path GE is SG, that is equal to length LG of that free space divided by mu 0 AG, since mu r is equal to 1 for free space. Similarly, reluctance of path BAFE S1 is equal to length of that path L1 divided by mu 0 mu r1 into A1, and reluctance of path BCDE is equal to S2 is equal to L2 divided by mu 0 mu r2 into A2. This is a series parallel magnetic circuit with an air gap. We can draw one electric circuit which is equivalent to this as we have studied earlier. in this circuit, the total current I is the sum of the current flowing through this path and this path. That is, total current I is equal to I1 plus I2. Similarly, in this magnetic circuit, total flux divides into two as phi1 and phi2. Therefore, total flux phi is equal to phi1, which is going in path BAFE, and phi2, which is going to the path BCDE. In this electric circuit, EMF across the parallel paths BAFE is equal to EMF across the parallel path BCDE. That is, I1 into R1 is equal to I2 into R2. Similarly, in magnetic circuit, MMF across these parallel paths are same. That is, MMF across BAFE is equal to MMF across BCDE. That is, phi1 into S1 is equal to phi2 into S2. In electric circuit, EMF E is equal to I into R. That is, EMF E for path BAFEB is the voltage drops in these two resistances plus the voltage drop in this resistance. That is, here the same current is flowing through these two resistances. So, I into R plus RG plus I1 into R1. As these two paths are parallel, the same EMF is there in this path also, or EMF E for path BCDEB is I is the same for these two resistances. So, I into R plus RG plus I2 into R2. Both are same as EMF across the parallel path BAFE is equal to BCDE. Similarly, in the case of a magnetic circuit, MMF F is equal to phi into S. That is, MMF F for path BAFEB is the seriously connected air gap and this main limb. That is, phi into S plus SG plus this series reluctance drop phi1 into S1. As MMF F for path BAFEB is the drop in the seriously connected air gap and this main limb, that is phi into S plus SG plus this limb phi1 plus S1. The same drop is coming here also, or MMF F for path BCDEB is phi into S plus SG plus phi2 into S2. As this MMF and this MMF are same, we can take either this one or this one. Both are same, as MMF across parallel path BAFE is equal to BCDE. Now, we will try to solve some problems on parallel magnetic circuits. It is given that area of cross section of the limbs A is equal to 2 cm into 2 cm. Number of turns is 500 and a flux 2 milliweber is produced in the right limb. We are asked to calculate the current required in this coil to produce that 2 milliweber in the right limb. The relative permeability of this steel magnetic structure is given as mu r is equal to 600. That is, A is equal to 2 cm into 2 cm, that is equal to 4 cm square, which is 4 into 10 raised to minus 4 meter square. Number of turns N is 500. Flux in this limb phi2 is equal to 2 milliweber. Phi2 is equal to 2 milliweber, which is 2 into 10 raised to minus 3 Weber. Since the paths C and D are in parallel with each other with respect to E, MMF across limb C will be the same as that across D, like parallel electric circuits. That is, MMF F1, that is across the limb C, is equal to MMF across limb D, which is F2. But MMF F is equal to phi into S. Therefore, this becomes phi1 S1 is equal to phi2 S2. Let this is equation number 1. Reluctance S is equal to L by mu into A. That is equal to L by mu 0 mu r into A, where L is length of the path and A is the area of cross section. Therefore, S1 is equal to length is 15 divided by mu into A, and S2 is equal to length of this path is 25 divided by mu into A. From equation number 1, phi 1 S1 is equal to phi 2 S2. So, equation 1 becomes phi 1 into S1 is 15 by mu A, which is equal to phi 2 into S2 is 25 by mu A, that is phi 1 into 15 by mu A is equal to phi 2 is given as 2 milliweber, that is 2 into 10 raised to minus 3 into 25 divided by mu A. In this equation, from left hand side and the right hand side, we can cancel mu A. Therefore, phi 1 is equal to 2 into 10 raised to minus 3 into 25 divided by 15. Phi 1 is equal to 2 into 10 raised to minus 3 into 25 divided by 15, that is equal to 3.33 into 10 raised to minus 3 Weber. So, we find that phi 1 is equal to 3.33 into 10 raised to minus 3, and phi 2 is given in the question as 2 into 10 raised to minus 3. Therefore, the total flux going from here will be the sum of these two fluxes, that is phi 1 and phi 2. So, total flux phi is equal to phi 1 plus phi 2, that is phi 1 is this much and phi 2 is this much, which is equal to 3.33 into 10 raised to minus 3 plus 2 into 10 raised to minus 3, that is equal to 5.33 into 10 raised to minus 3 Weber. See here, as path C and D are parallel, total ampere turns for the whole circuit is equal to the ampere turns required for path E plus ampere turn required for path C, that is F plus F1, or ampere turns required for path E plus ampere turn required for path D, that is F plus F2. That is, we have to take either F1 or F2 as both are parallel. That is, total ampere turns required is equal to ampere turn for path E, that is F plus ampere turns for path C, that is F1, or ampere turn for path E, that is F plus F2. Since F1 is equal to F2 as both are parallel circuits. Here the total flux is 5.33 into 10 raised to minus 3, and the area of cross section is 4 into 10 raised to minus 4 meter square. So flux density for path E is B is equal to phi divided by A, that is equal to phi is 5.33 into 10 raised to minus 3, and area of cross section 4 into 10 raised to minus 4. This is equal to 5.33 into 10 raised to minus 3 divided by 4 into 10 raised to minus 4, which is equal to 13.3 Weber per meter square. See the formula, flux density B is equal to mu into H, therefore magnetizing force H is equal to B by mu. MMF F is equal to H into L, but H is equal to B by mu into L, that is equal to B by mu 0 mu r into L. Therefore, ampere turns required, F is equal to B by mu 0 mu r into L. B by mu 0 mu r into L, that is equal to B is 13.3 divided by mu 0, that is 4 pi into 10 raised to minus 7 into relative permeability is given as 600 into length is 0.25, which is equal to 4420 ampere turns. Similarly, flux density in path D is equal to phi 2 divided by this area of cross section, that is B2 is equal to phi 2 divided by area of cross section, that is equal to phi 2 is 2 milliweber, that is 2 into 10 raised to minus 3 divided by area of cross section is 4 into 10 raised to minus 4. This is equal to 5 Weber per meter square. We know that ampere turns required, MMF, F is equal to B by mu 0 mu r into L, that is F2 is equal to B2 divided by mu 0 mu r into L2, that is equal to B2 is 5 Weber per meter square divided by mu 0 is 4 pi into 10 raised to minus 7 into mu r is given as 600 into length of path is 25 centimeter or 0.25 meter, 0.25. This gives 1658. Therefore, total ampere turns is equal to 4420 plus 1658. This is equal to 6078. Therefore, current needed I is equal to total Ft divided by N. This is equal to 6078 divided by 500, which is equal to 12.16 ampere. In this question, a ring of cast steel which is having an external diameter 24 centimeter, and it is having a square cross section of 3 centimeter side. Inside and across the ring, an ordinary steel bar 18 centimeter length, 3 centimeter width and 0.4 centimeter thickness is fitted with negligible gap. We have to calculate the number of ampere turns required to be applied to one half of the ring so as to produce a flux density of 1.0 Weber per meter square in the other half. We can neglect leakage. The BH characteristics are given below. For cast steel, it is like this. For ordinary steel bar inside the ring, it is like this. So it is given that the total diameter of the ring is 24 centimeter and thickness is 3 centimeter. So this mean diameter becomes total diameter 24 minus half of 3, 1.5 here and 1.5 here. That is 24 minus 1.5 plus 1.5. So mean diameter D is equal to 24 minus 1.5 plus 1.5. This is equal to 21 centimeter. That is 0.21 meter. Therefore, mean circumference is pi d, that is 3.14 into 0.21. This gives 0.66 meter. So total circumference is 0.66 meter. Therefore, length of path A or C is half of this. That is, length of A or C is equal to 0.66 divided by 2, that is equal to 0.33 meter. See, flux density is given as 1.0 Weber per meter square. From this table, for creating a flux density of 1.0 Weber per meter square, the magnetizing force required is 900. That is from the table for B is equal to 1.0 Weber per meter square, H is 900 ampere turns per meter. Therefore, total MMF for path C is F is equal to H into L, that is 900 into length of path C, that is 0.33, which is equal to 297 ampere turns. As the paths C and D are in parallel, the same MMF is applied across D also. Therefore, for path D, magnetizing force H is equal to F divided by L. See, in path D, same magnetomotive force F is there. So, 297 divided by length of this path D is 18 centimeter. That is 0.18 meter. This is 1650 ampere turns per meter. But we know that flux density B is equal to total flux divided by area of cross section, or flux is equal to flux density into area of cross section. So, flux through path C, phi C, is equal to flux density through path C into area of cross section of path C. That is equal to, it is given in the question that flux density is 1.0 Weber per meter square. So, 1.0 into area of cross section is 3 into 3, 9 centimeter square. That is 9 into 10 raised to minus 4 meter square. This is 9 into 10 raised to minus 4 Weber. So here the magnetizing force is 1650. From the table, for a magnetizing force of 1650, the flux density, corresponding flux density is 1.45 Weber per meter square. Therefore, for that ordinary steel bar fixed in the middle, B is equal to 1.45 Weber per meter square, as we got from the table. Area of cross section of this middle ordinary steel bar is given as AD is equal to 3 into 0.4 centimeter square. That is equal to 3 into 0.4 into 10 raised to minus 4 meter square. The middle bar flux density is 1.45 and area of cross section is 3 into 0.4 into 10 raised to minus 4 meter square. Therefore, flux through the middle path phi D is equal to B into A, which is 1.45 into 3 into 0.4 into 10 raised to minus 4. This is equal to 1.74 into 10 raised to minus 4 Weber. Therefore, total flux through A is equal to flux through C plus flux through D. Phi A is equal to phi D plus phi C, which is equal to phi D got us 1.74 into 10 raised to minus 4 and phi C we got as 9 into 10 raised to minus 4. So, 9 into 10 raised to minus 4 plus 1.74 into 10 raised to minus 4. This is equal to 10.74 into 10 raised to minus 4 Weber. So, flux through limb A is 10.74 into 10 raised to minus 4 Weber. Therefore, flux density in limb A is flux through A divided by area of cross section of A. That is, flux density through A is phi A divided by that area of cross section. That is equal to 10.74 into 10 raised to minus 4 divided by 9 into 10 raised to minus 4. This gives 1.193 Weber per meter square. For producing a flux density of 1.193 Weber per meter square for cast steel, which is coming somewhere here, the corresponding ampere turns or magnetizing force required is 1200 from the table. So, for producing this much flux density, the magnetizing force required is 1200. H is equal to 1200 ampere turns per meter. Therefore, MMF required for limb A is magnetizing force H into length of A, that is H into L, that is equal to 1200 into length is half of that circumference, which is 0.33 meter. This is equal to 396 ampere turns. Therefore, total MMF required is equal to MMF required for path A plus MMF required for path D or path C, as C and D are in parallel. We have to take any one of them. We found that MMF required for path C is 297 ampere turns and MMF required for path A is 396 ampere turns. Therefore, total MMF is the sum of ampere turns required for path A and path C or D. For path C it is 297 and for path A it is 396. So, total MMF required is equal to MMF for path A plus MMF for path C or D. That is equal to, earlier we found that MMF for path C is 297 and MMF for path A is 396. So, total MMF is equal to 396 plus 297, which is equal to 693 ampere turns. In this example, it is shown a rectangular iron section with a central limb. The central limb is having a length of 20 cm, area of cross section 8 cm square, while the side limbs are having 4 cm square cross sectional area and these are having a length of 32 cm. There is an air gap of 1.5 mm and the central limb is found with a coil which is having 500 turns. It is also given that for iron, for a flux density of 2 Weber per meter square, the value of H is 800 ampere turns per meter. We studied that it will be easier to solve the magnetic circuit if we are drawing an equivalent electric circuit. In this electric circuit, this battery, which is having an EMF of E, is equal to the magnetomotive force F generated by the coil. This resistance Rg is similar to reluctance Sg of air gap. Rc is equal to reluctance Sc of this portion, and the main current generated from here divides equally as IC by 2 and IC by 2, as they are equal resistances and parallel paths. Similarly here, the total flux generated phi C divides and goes to both direction as phi C by 2 and phi C by 2. That is half of the total flux generated. In this electric circuit, for the closed path HGFABH, this E is equal to voltage drop in Rg, Eg plus Ec plus EFABH, that is voltage drop in Ra. Similarly here, total MMF is equal to MMF in air gap Fg plus MMF in central path Fc plus MMF through this path FABH. So in electric circuit, E is equal to Eg plus Ec plus EFAGH. Similarly, in this magnetic circuit, total MMF F is equal to Fg plus Fc plus FAGH. We are given that flux in central path phi C is equal to 1.6 milliweber. Phi C is equal to 1.6 milliweber, that is equal to 1.6 into 10 raised to minus 3 Weber. As this central limb and air gap are in series, the same flux passes through this air gap also. That is, phi G is equal to phi C, which is equal to 1.6 into 10 raised to minus 3 Weber. Area of cross section of this central limb AC is given as 8 cm square. That is, 8 into 10 raised to minus 4 meter square. Air gap also we are having the same area of cross section. We know that reluctance S is equal to length L divided by mu into area of cross section A, that is L by mu 0 mu r into A, where mu 0 is the permeability of air or vacuum and mu r is the relative permeability of that material. Therefore, reluctance of air gap Sg is equal to L by mu 0 into A, as mu r is equal to 1 for air. This is equal to length of air gap 1.5 into 10 raised to minus 3 divided by mu 0 is 4 pi into 10 raised to minus 7 into that area of cross section 8 into 10 raised to minus 4. This is equal to 1492 into 10 raised to 3. We know that mmf F is equal to 5 into S. Therefore, mmf of that air gap Fg is equal to 5G into Sg. That is equal to 5G is 1.6 into 10 raised to minus 3 and Sg is 1492 into 10 raised to 3. So this becomes 1.6 into 10 raised to minus 3 into 1492 into 10 raised to 3. This is equal to 2387.2 ampere turns. Then flux density B in center limb, that is BC is equal to 5C divided by area of the center limb, that is 5C we know that 1.6 into 10 raised to minus 3 divided by area of cross section of central limb is 8 into 10 raised to minus 4 meter square, 8 into 10 raised to minus 4, that is equal to 2 Weber per meter square. See, in the question it is given that for iron, for a flux density of 2 Weber per meter square, the value of H is 800 ampere turns per meter. Therefore, in the center limb, for this flux density, H is equal to 800 ampere turns per meter. So, for center limb we found that H is equal to 800 ampere turns per meter and it is given that it is having a length of L. Therefore, Fc is equal to Hc into Lc. This is equal to Hc is 800 into length of center limb is 20 into 10 raised to minus 2. This is equal to 160 ampere turns. Flux passing through this outer path FABH is half the flux in the inner path, that is flux through FABH is equal to 5C divided by 2, that is equal to 1.6 into 10 raised to minus 3 divided by 2, that is 0.8 into 10 raised to minus 3 Weber. Area of cross section of this outer limb is given as 4 centimeter square. Therefore, flux density of this outer path FABH, that is BFABH, flux density through the path FABH is equal to flux divided by area of cross section, that is 5 FABH divided by area of cross section of the outer limb, that is equal to 0.8 into 10 raised to minus 3 divided by 4 into 10 raised to minus 4. This is equal to 2.0 Weber per meter square. It is given that for a flux density of 2 Weber per meter square, magnetizing force H is equal to 800 ampere turns per meter. Therefore, for B is equal to 2.0 Weber per meter square, H is equal to 800 ampere turns per meter. Therefore, from this formula, MMF for outer limb FABH, that is for this outer limb, is equal to H into L, which is equal to 800 into length of outer path, which is given as 32 centimeter, that is 32 into 10 raised to minus 2 meter. This is equal to 256 ampere turns. Therefore, total MMF is the flux for this air gap, that is 2387.2 plus for this center limb FC, that is 160 ampere turns, plus for this limb, that is 256 ampere turns. Total MMF F is equal to 2387.2 plus 160 plus 256, which is equal to 2803.2 ampere turns. We know that MMF F is equal to N into I. Therefore, current required to produce this MMF is I is equal to F divided by number of turns N, that is 2803.2 divided by 500, that is equal to 5.6 ampere. Hope this class also might have been useful to you. If so, please like it, share it and subscribe it by pressing that bell button so that you will be getting all the notifications of my future videos also. Thank you for watching. Bye.